Hello and welcome to the last in this series on summary videos on Diploma Programme Physics on topic 5. We're going to end off with magnetic fields and forces. First off, what is a magnetic field? Well, one can define it, or not really a definition, but we can say it's a region in which a magnet or a moving charge or a current carrying wire experiences a force. And here are some examples of what magnetic fields can look like. So here we have a bar magnet with a north and a south pole, and the field lines go from north to south, and they are more bunched up the closer you are to the magnet, and then they get more spread out the further that you are away. And the tighter the field lines are, the larger the field strength density. And so the field lines will go out of the North Pole and into the South Pole, and around the edges they will be curved like this. Now, turns out that if we have a current carrying wire, it will create its own magnetic field which is circular, and the further you are away from the wire, the weaker the field is going to be, so the lines are going to be more spread out, and the direction in which the field goes around the wire, either anti-clockwise or clockwise, is given by the right hand screw rule or the right hand grip rule, where your thumb is the current and the curl of your fingers gives the curl of the magnetic field. Now, a solenoid is a coil of wire, and if we have a current passing through the coil, depending on the way the coil is round, we'll have a magnetic field flowing left to right or right to left. The important thing in this context is that within the coil, the field lines will be uniform, i.e. they'll be parallel. Now, it turns out that there are two cases in which we can experience a magnetic force. One is if we have a current carrying wire within a uniform magnetic field of strength B, and the other case is if we have a charged particle moving at a velocity v in a uniform field. And in terms of notation, a cross in vector notation means that the field is going into the page, and a dot means the field is going out of the page. So if we have a length of wire L in a magnetic field with a current flowing through it I, and the magnetic field strength is B, then it will experience a force F, whose magnitude is given by BIL times sine theta, where theta is the angle between the current or the wire and the field. And its direction, because it's a vector quantity force, remember, it has a magnitude and a direction, is given by the right hand rule, RHR, where your thumb is the current, your first finger is the magnetic direction of the magnetic field, and your middle finger gives the direction of the force, and they have to be right angles to each other. Similarly, if we have a positive charge traveling in a uniform magnetic field, this time the magnetic field is pointing out of the page, the magnitude F is given by BQV sine theta. B is the magnetic field strength times the amount of charge times by the velocity of the charge times by the angle between the magnetic field strength and the particle's velocity vector. And the direction is given by the right hand rule, but you just replace current with velocity to give you, in this case the force would be directed downwards, and in this case the force would be directed to the right. Note that the direction rule only applies to positive particles, so if you have a negative particle you have to reverse direction. Reverse for negative particles, i.e. an electron. Reverse the direction of the force, that is.